All right.
Hi, my name is Yasmin, and I am the team leader for TouchTrainer, and I'm here presenting with my teammates, Jenna, Aiden, and Lindsay. So background on our project is that we're working on rehab robotics. So our goal is to make the first at-home stroke rehabilitation device for newly stroke patients. And so one thing that we have to focus on is something called somatosensation. So that is essentially the principle of connecting the feeling that you get when you touch your hand and also your awareness of your limbs in space. Also, when people have a stroke, depending on the area in the cerebrum where it happens, you can also have a loss of somatosensation in your right, left, or both hands. Previous rehab robotics that have worked with UCI have discovered that this loss makes robotic finger training ineffective, so the previous project that they were working on was not actually helping the stroke patients, which is the reason why we are on a first-year new project system for the next 7 years. With patients' loss of motor function, it typically affects their fingers up to their wrists and has a slower and weaker muscle strength in the arm. And another problem with current stroke patient rehabilitation is that it's really boring and they have to get to it. And so essentially it's, if you don't use it, you lose it. So if we don't have you actually effectively rehabilitating their limbs, then they're not going to gain that sensation back. Typically with patients' fingers, they're also clenched in a tight position, which is another thing that we have to focus on with our design, and that's called spasticity. So our goals and objectives is, like I said before, is that we're trying to make the first at-home stroke rehabilitation device. Our design technology requires that we have the patient sense their input through their hands. So we're blocking their view of their hands, so then they actually focus on feeling the vibrations under their fingers rather than seeing that one hand is moving rather than the other. This will be done in the context of an engaging game, which again goes back to the fact that we want to make sure that they're actually having a fun time and also getting their rehabilitation. Also, this should provide technology so that it's a portable cube that's ergonomic, easy to use, and lightweight, so that they can take it places, and also that it's universal to many different ages. And our overall objective for winter quarter is to continually finish the prototype and implementing changes for the prototype and testing so that we can make a better model for next year to bring onto for the next team for next year. So I'm going to pass my baton off to Aiden to talk about our responsibilities.
Thank you. So this is our breakdown for our team roles. So we have pseudocode, feedback, and music, and also creating the general code for the cube for our product. That's Aiden, Stanley, and Isa. And then since our team's small, we have people doing more than one job. So we have comfort, ease of use, which includes donning and doffing, and the user interface. We have Jenna, Lindsay, Michael, and Yasmin all working on that. And then our mechanical design, we have Lindsay, Michael, Isa, and Yasmin. Our prototyping, which includes 3D printing, which is what we're doing right now, is Yasmin, Jenna, and Lindsay. And then experimental testing / verification, we have Jenna and Yasmin doing that. Next is our subsystem breakdown. So we've divvied up everything into 4 subsystems: mechanical, user interface, code, and testing. So mechanical involves anything with the physical model, moving parts. So we have, to move each finger, we have 6 linear actuators. We need 6 because we intend to make this device work with both the right and the left hand. So when you flip it over, we're including 2 thumb actuators. So it's completely ambidextrous. That's why we have 6 vibrational motors as well to stimulate the fingers, because the vibrational motors will help with what you said earlier, the somatosensation. And we have 6 buttons to make sure the patient knows, or to test the patient's ability to recognize that the buzzing or the movement of their fingers. And then connections to the user interface. For user interface, it's about donning and doffing, so how the patient is going to put their hand in the device. There may be some challenges involving spasticity, the fact that the person's hands might not move well, so we have to take that into consideration. And we also have to take into consideration comfort and safety also. Next we have code, so control the system. We're going to make a game kind of like Guitar Hero, if you've ever played Guitar Hero before. So each finger will move, and then we'll have music playing at the same time, and ideally the same tempo as the fingers move. So we're going to use a Raspberry Pi to control that music plus the gameplay, actuating all the linear actuators, and then looking for their response, and recording the response data to see how well they perform. And then lastly, testing, where we verify what we've done works and that we can actually provide results, making sure the product is durable with like monkey tests, so it can handle like day-to-day use. Next, I'm going to pass this on to Jen.
I'd like to talk about the overall timeline. So for winter quarter, we've been mainly focusing on week 1 and 2 ordering these parts, and then we've been wanting to finalize the model and decide on 3D printing materials. Week 5, we began 3D printing our prototype. We've been making changes based off of what our prototype provides us. We still have been finishing up this prototype, and then we're going to start implementing testing on the prototype. By week 10, we hope to have a finished prototype, begin implementing more testing, and finalizing this CAD design based off of our prototype. As for spring quarter, we're going to begin adding electronic components and really finishing that coding for the electronic. We begin to have manufacturing methods for our final device. It'll be a second prototype really to move forward with, finalizing that CAD, building the product based off of that manufacturing method, finalizing the design, and by week 10 of next quarter having it built and completely ready to present. So the next thing I want to talk about is design requirements for improving loss of motor function, which is our overall goal, and it'll go into more specifically our design goals. So we want to have an engaging game that's similar to call and response. Your finger will sense the input, it will respond to the output. You need to stimulate tactile senses. This will be through a vibration motor disc. Challenge proprioception. This will be through an actuator. We want it to be ergonomic, so universal. All hands can use it. All ages can use it. So we want it to also be comfortable. This will also contribute to the overall dimensions and the materials used. We also want it to be comfortable in the sense that where they put their hands feel normal. We also want it to have specific design requirements, such as under 10 by 10 by 10, since it's a cube in inches. We want it to be able to we want it to be able to have a lightweight material, and we want it to also be under 5 pounds, which means they can hold it and not feel light or feel like it's too heavy since their arm is a bit weaker. And then we want it to be easy to use. Can they actually use it without the assistance of a medical professional? And then we want it to be able to sustain a 6-foot drop. So with all of those requirements, we'll move forward with how the engineering CAD fits that. I'd like to pass it to Lindsay.
So using the engineering design process, we've defined the problem, which is we want to retrain and stroke patients loss of proprioception and sense of touch. And we've planned the solutions. We've come up with a concept that includes drawings and brainstorming and calculations of how stiff your fingers are and what kind of forces are needed. Right now we're in the make a model stage. We have SolidWorks done, and it's changed quite a bit throughout the whole quarter. And then we've had freehand drawings, and we've started the 3D printing. With the 3D printing, it's kind of changed how our model and prototype is going. And then further, we will test the model. That's what she said, the monkey test. Can we use it on a day-to-day basis? Can we drop it off at 60? And then 3D printing failures has changed our product a lot. That's kind of like you're learning what works and what doesn't by 3D printing. And then we will reflect and redesign, which is also as we're going and prototyping. So these are the different types of designs we've had. Design 1, you can see that we want to put the thumb on the top, and we've actually kind of taken that out for now and focused on the other fingers. So this is our most current design, and we kind of come up with the puzzle design because of the 3D printing. And then, So the left side right now is the disabled hand. So all of these, the red will be moving out and moving your fingers. And then you will respond with the right side, which those will be push buttons. This is an exploded view, so you see the 4 different finger keys. And then there will be 4 different actuators for those. And then there will be probably a push button now for your thumb on the top and on the bottom so that it's ambidextrous. And the way we're doing this is 3D printing in Rankin Myers lab. We are using polyacrylic acid for the material, and then a 1.75 millimeter filament. And we might be changing to APA, or what's it called?
We originally wanted to use ABS, but our material will change based off of our final design, what material we decide on in manufacturing.
Okay. And so we can see that we changed our device because of our 3D printing. Before we had a 1.5 millimeter connection for the actuator, and we had a lot of issues with how it printed, and then we changed it and it looks a lot better now, and it connects a lot easier. And then this is one of our first prototypes. We obviously had to change it because of the 3D printing. We found out a lot of new ideas from it, so we changed it and made it a lot more sophisticated. And now I hand it off to Jenna for the testing.
For future testing, we really want to begin testing the vibration motor disc that we're going to be implementing. Currently, we have it for 2 to 5 volts. A regular cell phone uses about 3 volts for vibration, so we just want to have a code implemented using Arduino to double check that these vibration motor discs can be felt through the 3D printed material, and then based off of the manufacturing method, ensuring that the vibration disc can be felt through that material as well. We also plan on testing the prototype hand fit, so ideally we would hope to have a device that is universal, that can work for all patients, but this is quite difficult, we're finding, and our dimensions might change. A lot of hands can't actually reach the actuators, and so these are things that we need to see based off of trial and error and based off of testing. We may end up with 2 devices for 2 different sized hands, or we're hoping to find a solution to have 1 universal size, but that will all be based off of future testing once the prototype is completed. That should be all for that, and now I'd like to pass it to Yasmin for the bigger picture.
Thank you. So the reason why we really want to make sure that we actually do this is because, like we said before, there is no home device, or there is no actual device that's really good for stroke patients at the moment to train their somatosensation. And again, like we said before, we do not want it to require assistance from a medical professional. Additionally, we're going to have data collection so that we can use for further stroke rehabilitation research, so then it actually helps the doctors, so then they can also better help the stroke patients. Where it's also projected to be the first step in stroke rehabilitation for home devices, and also ideally the first device that will universally fit all hand sizes, given with what we learned after we've done more prototyping. And we also believe that this is very economically appealing because it's a lower cost training device, which also makes it more universal for more people. Additionally, for our budget and feasibility is that right now our budget is around $1,000, and the amount that we approximately spent right now is $250 with our actuators, with $70 each being the most expensive item that we've had to buy. Additionally, with feasibility, our 3D printed parts are printed for durability for the prototype. And also we have a very simplistic design because, like we said, that we want it to be available for many different ages, whether you're old or young. And additionally, with the puzzle piece structure, it allows for easy design changes. So with further testing, we'll be able to make it better for more people. So thank you for coming to our design.